Hello, this is Isaac Miller, and my lab experiment will be on internal combustion, and the concept is to demonstrate the combustion of an engine and calculate for the ideal volume of emissions from a gallon of gas. If you'd like to, you can pause and read out my script, but we're going to jump right into it. Alright, so the things you're going to need is a small Gatorade bottle or water bottle, a lighter, and safety glasses. And for this, we're gonna give it a 10 count of butane gas into the bottle, and since butane is heavier than air, it'll flow down into the bottle. So we're gonna count out for 10 seconds. And then place it on its side and ignite it from the side with your fingers out of the way, and you'll be able to see it burn. And so that demonstrated, you could see the burn start over here and slowly work its way to the end. Depending on how much gas you put, it might be a faster burn, but there's different air-fuel ratios to make it burn faster or slower. So what you just saw was butane burning in a cylinder, and that is representative of gasoline in a cylinder when it vaporizes or turns into a gas, and that's what the carburetor is for, because you can't get an efficient burn without it being a vapor or in a gaseous state. So to find the emissions that come off of a gallon of gas, we use the main ingredient of octane, which is 2,800 grams per gallon, and we can use that along with the chemical equation for the combustion of the octane to find how many CO2 emissions per gallon of gas are emitted through the exhaust pipe. So using that 2,800 grams of octane, we need to transfer that into moles. And so the molar mass of octane is roughly 114 grams per mole. So we inverse that to multiply it with the 2,800, and we get 24.56 moles of octane. And then from the moles of octane, we need to transfer that into moles of carbon dioxide. So we have our 24.56 moles of octane, and the ratio of moles of CO2 to moles of octane is 16 to 2, which is 8. So you multiply this by 8 and get the moles of CO2, which is 196.5. And then in order to convert that to our volume over here, we use the PV equals nRT equation. So we're moving from moles to liters. So our volume is equal to nRT over P, and so we use the 196.5 moles times a constant of 0.0821, and then we're going to say it's roughly 80 degrees Fahrenheit outside, so 300 Kelvin at 1 atmosphere. And if we do all this, the moles cancel out, the atmosphere cancel out, and the Kelvin cancels out, so we're left with liters. And our resulting liters of CO2 for 1 gallon of gas is 4,840 liters. So how does that rate of burn affect us in our daily lives? So we'll call this the piston, and this will be the cylinder walls, and the spark plug will be right up here. So that rate of burn can affect your ignition timing. So let's say this is compressing the gas right here, the piston, and you don't want your spark plug to go off at top dead center, which is the top of the piston stroke. You want it to ignite as the piston's coming up so that it has its main explosion or burn right at top dead center to push it back down efficiently. Although if your timing is too advanced and it ignites too early, it'll try to explode on the way up, causing the piston to be forced back down and that'll result in knocking in your engine, and it's just not very good for it. So you want to have the right advancement in your timing to have the most efficient burn possible and transfer that into work.